Okay, our last review, and then we'll meet on Monday for a final exam.
Why do we have to have this exam on Monday? That's what I wanted. What did I say?
I know who made the schedule, just determined, but I can guarantee you it's not my choice.
It's today. He said. That tells you how much on track I am. Monday. I really thought it was on Tuesday. She really did. She tried to tell me.
Okay, I will check our syllabus to make sure it says in the syllabus Monday from 10 to 12. Yes. Hannah is on top of that.
So you should put like
That's the day I'm gonna die, and you guys are gonna bury me. No, we're not. Hannah.
And then make it like a 20-point.
Okay, let us review for the exam. It will help us more than anything else.
Are we gonna get out early?
So, no, we're not going to get out early. We're going to try to cover as much to make it as easy as it can be for the exam. So, we've talked about reviewing all of the physics stuff, and I know we took longer on physics than we did anything else, and longer reviewing on physics than anything else, but that's because physics is the fundamental science here. We had physics ideas that showed up in chemistry, and showed up in geology, and showed up in astronomy. So now we're going to chemistry, and we have that periodic table. So once again, I will give you the same periodic table on the exam as you had on the chemistry exam. And you have, well, basically the same things that you had to know for that. So the nucleus, the center of the atom, has protons and neutrons. No electrons there, just protons and neutrons. Has a positive charge because protons have a positive charge and neutrons have zero charge. Then you have a cloud of electrons that's going around the nucleus. Early theories said that they were doing circles. That was actually a theory that didn't last all that long, like a decade at the most, when people thought that they were doing circles. Now we just say the electrons are in this cloud and we don't know what their paths are. But we have the electrons outside, and almost all of the volume of an atom is taken up by the electron cloud. The nucleus is a very small volume. The atomic number is the number of protons in the nucleus. That's a very important number. It's what tells us the kind of atom. And so you can just look at the periodic table, you find oxygen, you look up in the top right-hand corner of the one back there, and you see it has an 8. That's the atomic number. That's how many protons are in the nucleus. Atoms strive for neutrality. So if I have a neutral oxygen atom, since it has 8 protons in the nucleus, it should have an equal number of electrons orbiting the nucleus, so it should have 8 electrons. The electrons fill in shells, and the number of electrons in a shell is reflected by, well, the way we talked about them in this class. Yeah. The way we talked about them in this class is we would just say the number of electrons in a shell is the number of elements in a given period. So you have 2 in the first one, 8 in the second and third, and then 18 in the next 2. Yes?
On your notes, is alkaline earth metal supposed to be column 2?
Yes.
Because it's confusing because first you do periodic numbers for like the first 2, and then it's like 17, 18, 3 to 12. So that should be the number 2.
Yeah, okay. I understand you're saying Roman numerals. Some of them do them all in Roman numerals. Some of them, like this one here, do them all in numbers, and I switched between them. And I see the difficulty there.
Because I almost wrote down 11, and I was like,
there. Thank you.
Okay, it is 2. See, it was confusing.
Like I said, I understand. Okay, so atomic number, the number of protons in the nucleus, also the number of electrons that are orbiting the nucleus if it's a neutral atom. Now, we talked about the atoms that are like halogens. They have a high electronegativity. They really want to grab another electron to get a completed shell. The ones that are in the alkali metals, they have only 1 electron in the outermost shell. And they don't really care that much about it. They're happy to give it up for the most part. So they have a very low electronegativity. Also, make sure you know about the atomic mass. The atomic mass is fundamentally the number of protons in the nucleus plus the number of neutrons in the nucleus. And so atomic mass is telling us how much its total mass is, because a proton and neutron have about the same mass. Quantum theory simply means that, well, when we're using quantum theory in an atom, we are looking at the wave properties of an electron. Now, we are not studying quantum mechanics in this class at all, so that's all we really need to know, that we're studying the wave properties, and it results in only specific energy levels, which is where the word quantum comes from. There's only certain energy levels you can have for the electrons in the atom. Also, there's only certain other things, but that's the one that we talked about. And the distinct line spectra, remember wearing the glasses and looking at those lines? Those are caused by electrons falling from a higher energy state to a lower energy state and giving off a photon, that's the name we give for a particle of light, with energy equal to the gap difference.
That's what HF stands for, is gap difference?
No, E is the gap difference. And F is the frequency, H is a constant. So what it's saying is the energy difference between the two states, that's the gap difference there, is equal to a constant times the frequency. So if it's a bigger gap, it's going to be a higher frequency. Smaller gap, lower frequency. Okay, next chapter, atomic nucleus and radioactivity. Remember we did the lab where you had to roll the dice to simulate radioactivity. Radioactivity occurs because you have a nucleus that is in an unstable state. It's like something that's balanced, but it could fall over. There's no way in the world I'm going to balance this. But this would be like a radioactive nucleus, and it falls over spontaneously because it's not in a stable state. And when it does, there's lots of different things it can do, but there's only three we talked about. They can give off alpha particles, which is a hemonucleus that comes out of the nucleus of the atom. So the atom's nucleus gets smaller by 2 protons and 2 neutrons. Or you have beta, that is an electron coming out of the nucleus, which is confusing because there are no electrons in the nucleus. When you have a beta emission, you actually have a neutron that's destroyed, and it creates a proton and the electron. And so if I have like carbon-14, it has beta decay, it gets rid of a neutron, adds a proton. So if you take carbon and you add a proton, what is the atomic number of carbon?
Can you repeat the question?
That's the atomic mass. 6. The atomic number, and remember that's the important thing to be able to distinguish those. So you have the atomic number 6. If you add 1, the atomic number becomes 7, which makes it a nitrogen. So carbon-14 decays into nitrogen-14 by beta decay. And an electron comes out. So that's what the beta decay is the electron. And then gamma decay is when it goes from a higher energy state to a lower energy state, but the nucleus remains the same. So it's kind of like I have bricks, and the bricks fall over. Still the same number of bricks, just stacked differently. And it gives off energy the same as when we talked about the emission of the photons, giving off the energy in an electromagnetic wave with energy equal to the energy difference. So we have the alpha, beta, and gamma decays. They're named alpha, beta, and gamma because alphas are really easy to stop. Your clothes will protect you from alpha radiation, so you don't really have to worry about damage from alpha sources. You have exposed skin, well, that skin is going to absorb the radiation. Betas, electrons, those are harder to stop. To stop the betas, you're going to need, maybe some lead or some aluminum or something. Gammas are really hard to stop, and so you're going to need like something significant. X-rays are not any of these, right? But what do you do to stop X-rays? You go to the dentist, they give you?
Go behind a wall.
You go behind the wall, or they give you a lead apron.
And then, what is the things that they put in your mouth?
These days, they put a little CCD sensor, something like you have in your phone. Back in the day, it was a piece of film. X-rays are not the same as gamma rays because X-rays are coming from electrons falling from higher energy state to lower energy state in an atom, whereas gamma rays are coming from the nucleus. But Otherwise, they're pretty much the same. Gamma rays can have the same energy, low energy gamma rays can be the same as high energy X-rays. So the radiation you get when you get an X-ray is similar to the radiation you get with gamma radiation. Yes, Amber.
For the point under where it says no about radiation dose, is that supposed to
I
be
just
dose or
really-
dose?
It's supposed to be dose, but we didn't do that.
Oh, so we don't need that.
No. Okay, so in our experiment, we looked at half-life specifically. Half-life, the time for 1/2 of our sample to decay. It's all based on statistics, so in 2 half-lives, you don't have 2 halves decay. You have a half of the remaining, so you have the amount that remains is 1/2 times 1/2 is 1/4 after 2 half-lives. After 3 half-lives, you can have 1/2 times 1/2 times 1/2, 1/8 remaining. So make sure you remember that 2 half-lives does not mean a whole life. Yes?
Are there going to be repeat questions from the previous tests on the final?
The student-written ones, there will be lots of repeat questions.
But like the
When the ones that you write, there won't be.
I don't write anything.
ones from the
You
book will
write
not
some,
be
the textbook
repeated.
writes some.
Wait, some of the questions are from the textbook?
Half of them are from the textbook.
Like from the
and half of them-
homework or from what part?
From the textbook has a
There's
set
a
of test
test
questions that they
questions.
consider fair questions based on the textbook.
Like in
Wow.
our book or just in your book?
That would have been
Well, they're not printed in either book. They're ones the textbook publisher provides.
Okay, I was gonna say.
But you always check them to make sure you cover.
I check them to make sure I cover them, yes. Because, otherwise that would be kind of a wicked test. So, did I memorize the entire textbook? Yeah, that wouldn't work. So, the ones that are student-written, you'll see a lot of those. The ones
Okay,
that
yeah,
are
that's what I was
textbook-written,
asking.
there won't be many.
Okay.
There may be some repeats, but not a lot, because it's a much bigger to choose from. So make sure you understand what half-life means, and so you can say something like, you find a bone and you check out the amount of carbon-14 and it has 1/16 of the amount of carbon-14, well, it's carbon-14 to carbon-12 ratio, that we have in the air. Approximately how old is it? It has 1/16 when it happens. 4 half-lives, right. Because it's 1/2 times 1/2 times 1/2 times 1/2 to get to 1/16. And I wouldn't give you anything other than an even multiple of halves. So you can just go 1/2 times 1/2 times 1/2 to get to. Nuclear fission and fusion.
Did we talk about that?
I don't think we talked about nuclear fission and fusion either. I'm going to cross it out. We probably did a little, but
How long is the test compared to a normal test?
it'll be probably around like 80-ish questions.
Okay, so less than 100.
Yeah, it'll be less than 100.
What do we have usually?
They're usually around 50.
Okay. It's not that bad.
So less than
Okay, some vocabulary words for chemistry. A chemical. What is a chemical?
Anything.
Except for vacuum. Anything made of atoms. Exactly. Okay, what is a molecule?
It could be a.
Isn't it a combination?
Yeah, it could be. It could be.
It could be a compound.
Could be a compound. Could be a single element, right?
Unit.
A single
Yeah.
unit of something.
Okay, stuff. How's that?
Duh.
A molecule. So you could have like helium. Helium alone is a single molecule. Or you could have H2. 2 hydrogen atoms is a single molecule.
What H2O?
H2O is another.
Single unit what?
A single
So if it
unit of
doesn't have
stuff.
a number in front of it. So if it had a 2 in front of 2 H2O.
That'd be 2 molecules. Okay, what about an element?
Element. It is
Nothing made
a
of
It's
single
pure
type of atom.
substance.
A single type of atom. So examples here. Well, the first 2 I did. Helium, H2, those are both elements. Or what's something, well,
So do we
ozone.
need to know the elements that go with this thing?
All of those are elements. No, you don't. I'm just giving you examples.
Oh, okay.
Because you might have a question that says, what's an element? And I want you to see some examples so you have the pattern matching idea of, oh, yes, if it's all the same type of atom, no different types of atoms, then it's an elemental compound. What's a compound? I said elemental compound.
It is two or more
Yeah.
atoms.
As far as we're concerned, elemental compound doesn't exist because compound's going to be two types of atoms.
Bryson.
It wasn't me.
For example, H2O has hydrogen, has oxygen, two types of atoms. Or,
Can a compound have two or more? types
Yes,
of atoms,
yes.
or is it only two?
so you could have, what's something with three?
H3.
Oh,
Oh, I see what you're saying.
ammonia.
Something you should,
That's C2 or C3? C2H5.
What is that?
what is that? That's ethanol.
Ethanol?
As you say, something you should never drink.
Oh, okay.
I think-
What's
Something you
salt
should
again?
Well, it depends on which type of salt. Table salt is NaCl.
NaCl.
Or you could have something like,
Sodium chloride.
sodium nitrate is also a salt.
Is it sodium chlorine or sodium chloride?
Chloride. Okay, so naming convention. Naming convention. We learned to take the first element on the periodic table, the one on the leftmost. So if it's Na and Cl, the leftmost one is sodium. Then we take the other one and we change N into I. So that's why it's sodium chloride or hydrogen fluoride. So remember the naming convention and the subscripts. So like if it's H2O, how would you name H2O other than water? It's common name.
Hydrogen oxide.
Dihydrogen monoxide. The reason you have to put the di and the mono is because you have other compounds with hydrogen and oxygen that can also exist. For instance, H2O2, which would be dihydrogen dioxide. I almost said dimonoxide. Was it?
Is that still a type of water?
No, that's actually what we call peroxide.
Really?
Hydrogen peroxide, to be exact.
Just because that has one more oxygen.
So hydrogen peroxide is H2O2.
Put it on your cuts and it bubbles up.
But it kills cells, so don't do that.
So be
Oh, I
able
did
to
all the
name
time
simple
also.
compounds.
So did I, but they say you should. What?
When you say be able to name simple compounds, is that what we were just doing? Like
That's what we were just doing, yes. Yes, that's the bottom thing here. What is a mixture? How's a mixture different from a compound?
It's, you can see the difference.
Two types of mixtures, homogeneous and heterogeneous. Heterogeneous, you can see the difference. Homogeneous, you can't.
They can
Like
be
milk,
separated.
milk and ocean water.
They can be separated physically.
I think milk and ocean water actually would be homogeneous.
Stuff floating
But,
around in
but,
it.
okay,
Well, but it's not milk.
Salsa is.
Salsa.
Okay. See, if you put milk with ocean water, it's going to mix. If you look at ocean water, you have, kelp in it or something.
Yeah, that's what I meant.
Okay. Oh, did you say kelp and I heard milk?
No, I said
Just trying
ocean
to
water,
say
it has stuff in it,
Okay.
like particles.
So mixture is two or more. And so this one here should have been or more as well. Two or more compounds mixed together. And you had, as we said, homogeneous or heterogeneous. Homogeneous, you can't tell that it's mixture. It looks like one thing. Heterogeneous, you can see the difference. So milk is a mixture. It's a mixture of fat globules and water. But you can't see the difference, so it's homogeneous. That's right.
I thought that the difference between homeo and hetero was that homeo was stuff that's mixed together that's the same. And then hetero is mixed differently.
Well, not for these naming conventions.
Isn't that what it was last time we learned about this stuff?
No. It was, I mean, we had pizza as an example. Okay, alloys. Alloys are a special kind of mixture, if you will, because alloys are metals where you just replace one type of atom with another type of atom. If they're both metals, you can just mix them pretty freely and make all kinds of great chemical properties. Physical properties versus chemical properties. The hardest part of that one lab was, is this a chemical or a physical change, right? Chemical changes is when you're changing bonds. So rust, which we later learned was an example of an oxidation reaction, where you oxidize iron. It's a chemical reaction when it rusts. It also produces a physical change because it changes the color and the texture. So chemical changes often result, almost always result, in physical changes. But if it's just a physical change without a chemical change, then we call it a physical change. So when water freezes and becomes ice, we call that a physical change because it's still H2O. It didn't change the chemical bonds. But it changed what it looks like, what it feels like. How atoms bond.
Wait, so what's in a
Excuse me?
what's in what?
An alloy.
An alloy is metals where you mix two types or more than two types of metals together. Okay, electron dot structures. Let's say I have carbon. How do I decide what to do with the electron dots if I'm going to do a Lewis dot structure? What's the first thing I have to determine?
How many dots it has?
How many dots it has. That's the first thing you have to determine.
Valence electrons.
The valence electrons. So if we look at carbon, how many electrons does carbon have, first of all? 6. And how many of those are the valence ones, the ones in the outer shell? No, you were right the first time, though.
6? 4?
4.
4. That's
Right. You said, oh, like you were wrong. And I was like, no, you were right. You were right. So it has 6 electrons, 4 valence electrons, 4 in the outer shell. So I have 4 electrons that I'm going to put around it. And then I put my electrons, 1 per side. And then if I had more, then I would start doubling up. So if I were to go to, let's say, oxygen, how many valence electrons does oxygen have? 6. No, it's 6. It's 6. You can just count on the second row. It's the 6th one across in the second row. And so the oxygen is going to have 1, 2, 3, 4. Then we start doubling up 5, 6. And so it has 2 lone pairs for bonding. And then the others are completed, so they're not going to bond. So only the lone pairs are available for bonding, which I probably shouldn't put circles when I have oxygen, which also looks like a circle. So now if I want to form a bond between oxygen and something, let's say oxygen and hydrogen. Simplest question I'll ask today, how many valence electrons does hydrogen have? 1. Because it's element 1. If it's neutral, it has 1 electron. So there's my hydrogen. I bring my oxygen to bond with it, and they're going to, too far, move. Okay, there we go. They're going to share an electron from each. And so there we have a hydrogen-oxygen bond. That's what the dot structure is useful for. I still have 1 electron of the oxygen that can be shared with something else for bonding. So I can put another hydrogen there and have oxygen bonded to 2 hydrogens. Now all of my electrons are paired up. And so now we're done. We have a nice stable molecule of H2O, or dihydrogen monoxide, or water. What kind of bonds am I doing here with their sharing electrons? Covalent. Did you say it? Great. So the electron dot structure is what we use when we're talking about covalent bonds. Not when we talk about ionic bonds. Because what's an ionic bond?
Electrons.
You take an electron off of one and give it to another. So if I have hydrogen and fluorine has a high electronegativity, hydrogen has a low one. The fluorine says, hey, I would really love to have your electron. The hydrogen says, take it. And so the fluorine grabs the extra electron, so now it has a negative charge. The hydrogen lost its electron and now has a positive charge. So we have one thing positive, one thing negative. From physics, we learned about the electrostatic force that opposites attract. And so the two are attracted together because one's positive, one's negative. That's the ionic bond. Now, these top two bonds are chemical bonds. The rest of these here, well, let's not include metallic. Metallic stands alone. The rest of these here are bonds between molecules. So if we talk about an ion dipole bond, we don't have ion-ion bonds because those would be covalent bonds. But if we have an ion dipole, then we have, if it's a dipole, one side's positive, one side's negative. And so we saw examples of the ion dipole bond in our experiment when we had the balloons. You brought the balloon up to the wall, the balloon was charged, so it would be an ion. The wall had dipoles, the dipoles reorient so the side that's attractive is closer, and since the electrostatic force is inversely proportional to separation, that is, we saw from the review on Wednesday, it's proportional to 1 over the separation squared, then the side that's closer is going to have the stronger force. And since the closer side is going to be the attractive one, you have a net attractive force between the ion and the dipole. And that's the strongest of these 4 forces that are between molecules. The next one's dipole-dipole. If the tips of my index fingers are both positively charged, if I bring my index fingers close to each other, the tips are pushed away from each other. So those are pushed away. What happens is the tip of one, the positive, is close to the tail of the other, the negative. And then the closer charges are attractive, so it's attracted and comes together. And so that's what forms the dipole-dipole bond. And that's what gives us our, what does ubiquitous mean? It's a word I like. It's everywhere. So we have these hydrogen bonds that are everywhere. For instance, hydrogen bonds are what creates ice. Ice is created when you have the hydrogen and oxygen. It's not a symmetrical bond because the oxygen is more electronegative. The hydrogen is negative, which means that the shared electrons aren't shared equally. The oxygen is a pig, and the oxygen is taking more of that electron. And so the oxygen has a net negative charge, whereas the hydrogens have a net positive charge. And so you have a dipole moment for the water molecule. And so when you cool it down, you'll have other water molecules that come by and a hydrogen says, hey there, I'm happy to meet you. And bonds like that. Now that's not the same strength at all as the bond between the H and O in the water molecule. But it's a strong enough bond to make ice a fairly strong material and to make it so the melting temperature of ice is a higher temperature than it otherwise would be.
Yeah.
Go ahead.
So you said that the top 2 were chemical bonds, and then what did you say?
They're I can't remember if it's inter or intra. I always get it confused. It's intramurals, but I get them confused. But so that's why they're between molecules. They're forces acting between, not within. And that's the problem. Inter and intra, one is within and one is between. Then dipole-induced dipole. Dipole-induced dipole is I have a dipole that comes near something, and it's going to cause the charge in that thing that was originally uniform to be distorted, so it becomes an induced dipole. And then that induced dipole is attracted. That's a pretty weak force, but not as weak as the induced dipole-induced dipole. Induced dipole-induced dipole, I take two things like, let's say, two helium atoms. They're symmetrical distributions. There's no dipole moment. If I bring them both toward each other, their negative electron shells are going to repel each other. And so they're going to start having a dipole moment. Well, if something else comes by when it has this dipole moment, it can have an induced dipole and they can bond. So induced dipole, it's a really weak force. The stronger the force between molecules, the higher the boiling and freezing temperatures are going to be. The weaker the force between molecules, the lower those are going to be. Because it'll take more energy to get them apart if you have a strong force. The stronger the force, so the closer you are to ion dipole, or the farther you are from induced dipole in that list, the more they're held together, so the higher the temperature is going to have to be to break them apart. So they're going to freeze at a higher temperature. They're going to freeze and melt at a higher temperature. They're going to boil at a higher temperature. Okay, the bottom line on this, be able to identify what a polar bond is and why this is important. Well, we've talked about that. How do you determine if a bond is covalent or ionic? You look at the electronegativities. If the difference in electronegativities is less than 0.5, then it's covalent. If it's more than 2, it's ionic. If it's between 0.5 and 1.6, it's called a polar covalent. Like, what is that word? I knew it was on the screen. A polar covalent bond. And you ask, what about 1.6 to 2? Well, 1.6 to 2 could go either way between ionic or polar covalent. And electronegativities. Where are the electronegativities large?
The most electronegativity is fluorine, so in the halogen.
Okay, the highest electronegativity is in the halogens. And top right is the highest electronegativity, bottom left is the lowest electronegativity. Sizes, how does sizes go? I know we've passed this already, but.
The biggest is the bottom and the smallest is at the top.
Okay, bigger are left and bottom, not counting the ideal gases. Or actually, no, the electronegativity, not counting the ideal gases. Smallest are the right and top.
This is nucleus or
The atom.
atom?
Nucleus, it just goes in order reading down the chart. Okay, mixtures. So we've already talked about all of these words. Don't have to go over them again. Solutions. We talked about the concentration of solution. We only used one concentration, the molarity, which was the number of moles per liter. Now, what do we have on top in that concentration? Number of moles of what?
The solute.
The solute, the thing that's dissolved, which is the minor component. On the bottom, we have volume in liters. Liters of what?
The solution.
Of the entire solution, which includes the solvent, which is the major component, and the solute, the minor component. So this is number of moles of solute over the liters of solution.
What is a suspension again? A suspension?
A suspension is when you have one type of thing suspended in another. So the example I used in class was Amy's colloidal silver. It's a colloidal suspension. You have little, I'll call them droplets, but they're obviously not liquid, of of silver. I hope it's not iron, just because she pays enough for that stuff. Little silver balls and water. And the silver balls are ionized. That is, they are, in this case, I think they are probably having extra electrons. And so with their extra electron, then the charge repulsion keeps them from just coming together at the bottom by gravity. And so they stay suspended, but they don't really mix, they're suspended. So it's a homogeneous mixture. Okay, saturated means you have as much as it can hold. So in our experiment where we had to see if stuff dissolved in water, it was really frustrating because it didn't completely dissolve. If it dissolved a little bit, and then we had a saturated solution, meaning that we had as much dissolved as it will hold. And then if you raise the temperature, what happens to almost every material?
I understand in the middle, we're trying to take notes.
If you raise the temperature for almost every material, it will then be able to hold more, and so you can dissolve more material. So that was the second test we did. We heated it up to see if it dissolved more or not. And there was one thing, acid nitrate, I forgot, that didn't change it, how much it can dissolve. Air is a good example of this. We have water in the air. And when the air is saturated with water, that means it can't hold any more water. You start forming clouds because you have droplets that start forming in the air. And of course, if those droplets come down, we call it rain. But clouds are droplets of water that form because you have a saturated atmosphere. If temperature goes up, air can hold a lot more water. So the saturated air, you heat it up, suddenly it's not saturated anymore. So if you take a cloudy region and it gets warmed up, the clouds will dissipate because suddenly the air can hold more water. Or if you take the opposite, you take moist air and you cool it down, suddenly a cloud forms. So growing up at the beach, we saw this happen all the time. We had morning overcast, morning fog we called it, and then it would burn off because the air heats up, the water goes into the atmosphere, is fine. In the evening, we had an evening fog because it cools down and the water then condenses again. What is a mole?
An animal on the ground.
In chemistry, I'm going with the two people who are answering chemistry here. It's a number of molecules. That number you don't have to have memorized, but it's 6.022. So a mole is that many molecules. It has a reasonable definition, but we won't even go there. You're either part of the solution or you're part of this precipitate. What's the precipitate?
Well, I think of precipitation.
Yes, that's a very good analogy because that's what the word means still.
Yeah.
Precipitation is water doing what?
Condensing, I should say.
Okay, the words I want, because they match here, is falling out of the sky. Precipitate is the stuff that falls out of the solution.
That's when it turns from gas to liquid, right?
No, gas to liquid is condensation.
Condensation. And then evaporation is liquid to gas.
Yes.
And
Precipitation is falling out of solution. So the precipitate, like if you mix hydrochloric acid, what does it mean if it's an acid?
very
Low
low
pH.
pH.
Okay, it has a low pH, a pH that's less than 7. And what did you say?
That's what I said.
That's what it said.
That means it has hydrogen, or it wants it.
That means it has more hydrogen ions. So that's what an acid is. So hydrochloric acid. And if I mix that with NaOH, don't remember what the name for that is. but it's a base, then sodium hydroxide. Yeah. If I mix sodium hydroxide and hydrochloric acid, I'm going to have a precipitate, what we call a salt, that's formed from the sodium ions being bonded to the chlorine ions. What kind of bond do I have between sodium ions and chlorine ions?
Ionic.
Ionic. So you have an ionic bond holding these two things together that precipitates out, and that's the definition of a salt. It's the ionic compound that is produced when you mix an acid and a base. Okay, with detergents, how soaps and detergents work to clean our clothes and hands. The long and the short of it, detergents are just harsher versions of soaps. You have one end that is a polar element, and then you have a non-polar tail. And so water being polar molecules, the polar side will be attached to water molecules. And then the non-polar sides will form the very weak induced ion bonds with grime. And so you have a bunch of these tails that attach to grime, and you have the heads that attach to water, and then they pick that grime up and carry it away. That's the way soaps and detergents work. So they lift and remove, as the commercial used to say. I don't know if you guys were even alive when that commercial was on TV. Then we had how chemicals react. So we learned a little about reactions. We have to be able to convert from atomic mass units to grams. Well, obviously I'm going to give you the number for that. That is, 1 atomic mass unit. U is actually what we use now. I still go back to when I was in high school and college, it was AMU instead of U. 1 atomic mass unit is equal to, and I'll give you this number. It's 1.6, I don't remember any more digits, times 10 to the minus 27 kilograms. Or, excuse me, times 10 to, yeah, that's right. So I'll give you that number, but you have to be able to say that. Okay, so if I have carbon with 12 atomic mass units, then that's going to be this many kilograms. Well, there's an easy version that we can use of 1U material, that is Avogadro's number times 1 atomic mass unit, has a mass of 1 gram. So if I have 1 mole of carbon, since it has 12 atomic mass units, 1 mole of carbon has a mass of 12 grams. And that's actually how the mole is defined, is from that relationship between mass of atomic mass units and grams. So you'll need to be able to say, okay, so if I have 10 grams of carbon 12, then I have 10 grams divided by 12 grams per mole is, that'd be 10, 12, so 5/6 of a mole of carbon 12. You need to be able to do those calculations. And then if I have a chemical reaction, remember how we balanced chemical equations, reaction equations? So we have to have the same number of atoms on each side. So something, trying to think of a chemical reaction offhand, which of course, it's always hard to come up with one on the fly. Yes. I truly am drawing blanks when I try to come up with a chemical reaction.
Oh, do a combustion. Those are my favorite kind.
I'm going to do the one I said. That's chemical reaction I already talked about. This one here is kind of simple because it's already balanced. You need to calculate how many H's do I have on each side. How many H's do I have on the reactant side? The reactant is the left side? How many H's? 2. How many chlorines? And how many sodiums? And how many oxygens? And then we look at the resultant side, and we have 2 hydrogens, 1 chlorine, hydrogen's chlorine, yeah. 1 sodium, and 1 oxygen. So it's balanced because we have the same number of atoms on each side. Obviously, you're not going to get something that simple. It's going to, a question like this will say, what numbers do you need to have in front of each molecule to make it balanced? And you just go through and you say, okay, how many do I have on this side? How many do I have on this side? What ratios do I need to have for the elements? For the molecules. Activation energy. Chemical reactions happen, of course, but usually there's an energy you have to put in before the reaction can start. And so that's called the activation energy. So it's a barrier. So if I take, hydrogen and oxygen and put them together, it doesn't blow up. What do I have to do to make it blow up? Yeah, I have to introduce heat. We have the 3 sides of that fire triangle. You have the fuel, the hydrogen, the oxidizer, the oxygen, and then you have the heat that makes the reaction start. So the activation energy is why we have to have that heat. But if we put in a catalyst will lower the activation energy. So in a chemical reaction that I like to talk about with this is what goes on in the atmosphere, where we have ozone that absorbs ultraviolet light, and that energy from ultraviolet light will make it break apart and form oxygen. That's good because it absorbs ultraviolet light. It's protecting us from UV radiation. But if you put it in the presence of a halogen, the halogen will catalyze the reaction. It'll make it so it requires less energy to make the reaction go. And then the energy from a visible light photon can be absorbed, not just ultraviolet. There's lots of visible light coming from the sun, so you have lots of breakdown of the ozone, and that's why we try to limit our halogens that we are emitting to the atmosphere in refrigerants. So the catalyst is something that lowers the activation energy, but is not part of the net reaction. Now, I showed you in class a reaction that came in 2 or 3 lines, and it had a catalyst, and the catalyst actually participated. So you start with the catalyst, and then it becomes part of one of the molecules in the reaction. But when the reaction's all done, it spit the catalyst back out unchanged. And so you started and ended with that catalyst. So it's not technically necessary because it was there at the beginning and there at the end. It's not consumed, but it lowers the activation energy to make the reaction occur. So catalysts are something that lower the activation energy that are there at the beginning and at the end, but they may disappear in the middle. Exothermic means you giving off energy. An exothermic reaction is where the net result is you're giving off energy. Things get warmer. Endothermic is the opposite. It absorbs energy. An endothermic reaction is going to make things get colder. Endothermic reactions don't normally just go because you have to put energy in to make them occur. But you can get the right materials, the right chemical reactions, and you can make the little ice packs that we use at sporting events that you just store them forever. When somebody gets hurt, you take it, you snap it. It has an endothermic reaction that makes it suddenly get very cold. You put it on the person, and they have cold packing. So that's a good example of an endothermic reaction that we use. Exothermic is just the opposite. You have hand warmers that you can buy that are the same thing. You keep them stored forever, You want to go skiing, it's cold out, so you take a hand warmer, you activate it, put it in your glove, and that exothermic reaction goes on. They make them so they're slow and reactive. So for like 8 hours, it keeps releasing heat as the exothermic reaction continues. Oh, we didn't get to chapter 18, acids and bases, the redox. And then, of course, we have the last two sections that I simply am not going to have time to review.
Is this gonna be on Moodle?
Yes, it is already.
Can you, like, is it possible if you have time in your day to write the stuff that you would have written, like if we'd gone through? Does that make sense?
Yeah, I understand what you're saying. Yeah, to continue to annotate it. Yeah, I can do that.
Because I think that would be really beneficial.
All right, have a happy Sabbath. Please don't study on the Sabbath hours.
Will
And
you
I'll
be
see you in
available-
class Monday.